Try doing these problems. Okay. We are now going into material close to stuff but that we use in quantum field theory and particle physics. Okay. And what I showed was the following. We showed that to find Lie algebra, of G, okay, what we do is write G of T, okay, basically as some G of epsilon as identity plus epsilon alpha G L alpha, okay, infinitesimally, okay, and find conditions on L alpha from G. Okay. G is given to you, it may be some matrix group, okay, then you find the conditions and write the Lie algebra. Okay. Then, so this is a basic, then what we found was, okay, call it G0. Then given Lie algebra, okay, given by L alpha L beta is C gamma alpha beta L gamma. If gamma, okay, some any element L alpha going to gamma of L alpha gives a representation of Lie algebra, that means this gamma is fulfilled C gamma alpha beta gamma L beta L gamma. We have the converse that then, okay, this mapping gamma of L alpha, say gamma of L going to exponential T gamma L. L is any element of the Lie algebra. Okay. So this is an element of the group, it is exponentiated, okay, generates a representation of G0 bar, the universal cover, okay, and you have to check, okay, so this is the, but this is exhaustive, that we get all representations of the group this way, okay, nothing is left out. Okay. Now, it's pretty obvious remarks, okay, that call this representation gamma. Okay. Gamma is IRR if and only if the original gamma of L gamma is IRR. It's almost obvious. IRR is a statement about invariant subspaces. Okay, so this is a statement that one has no invariant subspace if the other has no invariant subspace. Okay, and yeah. Then there was also the remark. I should not forget the important things. Okay. Yeah. I have already showed you that the direct products of groups generate direct sums of Lie algebras. Okay, that we also saw, no? If you take Cartesian products of groups, okay, to get new groups, their Lie algebras are simply direct sums. That is almost obvious. Okay. Now, I gave examples. Let me consider, we already considered SO3 in a particular way, okay, SON, okay. We considered this, okay. The Lie algebra is basis for the Lie algebra of SON is normally written as Mij. Okay. This is a basis, okay, where I is less than j and it goes from 2 up to n. Yes, 1, 2. So it is, so is NC2, so n into n minus 1 over 2, okay, which is a dimension of SON. Take any distinct pairs, okay. This is antisymmetric, so you get the dimension is, we saw this, no? In defining representation, we saw what this is, m mu nu ij was delta mu I, delta nu j minus mu to nu. These are antisymmetric matrices in the defining representation, and I should write also the commutation relations. M mu nu m lambda rho is delta nu lambda m mu rho plus delta mu rho m nu lambda minus, okay, antisymmetrized, no? Delta minus delta mu lambda m nu rho minus delta nu rho m mu lambda. This is a canonically you are writing it. By the way, once you have found this expression from here, when you look for representations, you forget about it. Okay? This one, okay? This is in the defining representation, and we use it to find the Lie algebra. And once we have got it, we should keep just the Lie algebra. Okay? Now, I want to spend today SUN. Because of its particular importance. Okay? So, in the defining representation, okay, what do I write? G is in SUN, so G of t, shall write as exponential t some u in SUN, and I want to SU2, I think we did already, but anyway, it's better to do it SUN. Then unitarity says G of GT dagger GT is 1. Unitarity, which says by expanding it to linear order, u dagger plus u is equal to 0. Right? From expanding in powers of t. And secondly, determinant of g of t is 1 implying trace of u is 0. Okay. So these are traceless matrices which are anti-Hermitian. Okay. So what we do is, okay, let still we are in a different representation, and A rho sigma ij is delta rho I delta sigma delta rho I delta sigma j. I just want to make sure I get the yes. Okay. These are just the matrices where in the row and sigma column has entry 1 and it is 0 elsewhere. Okay. Right? If rho is in the row column and sigma, is only one in that matrix. There is only one place, okay, where it is there is a non-zero entry. Okay. If this is 1 2, it is at the position 1 2 and so on. Okay. So this is a basis. Okay, be a basis for n cross n matrices. I am trying to go towards that equation. I am trying to find out these equations, okay, basis, but before that, okay, we notice that A rho sigma A alpha beta is, I think, delta rho beta A alpha sigma minus delta alpha sigma A rho beta. Let me get the, you can check it. This is up to a sign this is correct, but this is all due to work of Okubo. So this is a nice tensor notation with one upstairs index and downstairs index, and it goes I may be wrong by a sign, you can work it out. Huh? I. These are, I will do it, I will take care of it. These are not anti-Hermitian. No, they are neither Hermitian nor anti-Hermitian. I will find them later. Okay. So this is all n cross n matrices. Okay. Then, so we can now do following, okay, to make them traceless. Consider B rho sigma, which is A rho sigma minus 1 over n delta rho sigma. I think I wrote SON times unity. So this is traceless. Okay. So trace of B rho sigma will be trace of A rho sigma, which is 1, right? It has only A rho sigma, there is only one place where it will contribute, minus 1 over n. Okay. Wait, how does it go? It's not 1. It is trace of first one, let's write, is summation I, okay, A rho sigma I minus 1 over n delta rho sigma n. So we work it out. Okay. This one I am summing over I. Okay. So let's say there are two cases. That's why I should be careful. Rho is not equal to sigma. This is equal to 0. Rho not, this is 0 and this is, rho is not equal to sigma, this is I, so it is 0. Okay. If rho is sigma, so any value, for the corresponding value you get the right hand side, For the corresponding value I get 1 here minus rho equal to sigma 1, it is 0. So B's are traceless. But you should notice one thing, note, summation rho, B rho rho, these are not linearly independent, because if I do this, this is summation rho, A rho rho minus here, what will happen? I will get n is 1. Okay. But A rho rho is just one entry along the full diagonal, so this is 0. Okay. So B's are not so B's are not linearly independent. There are only n squared of them, n squared minus 1 of them. Okay. So only n squared minus 1 of them are so. So what the accomplishment with B is that I have taken into account this trace condition. The unitarity condition is the following. Okay. So I would say that B is okay. Now, as for A, what we have to know what is B rho sigma dagger. B rho sigma dagger, if you go back here, okay, by definition, B rho, I am taking the dagger of B rho sigma. I should complex conjugate, but these are real, transpose, so it will exceed J and I. So what will happen is I will get B sigma rho. And the commutation relation, so I can say that the Lie algebra, so we can say that the complexified Lie algebra let me call it SUN is complex, I am allowing complex coefficients is spanned by B rho sigma, okay, which fulfill the conditions B rho sigma dagger is B sigma rho and summation rho B rho rho is 0. Okay, how many of them are there? It is exactly n squared minus 1 of them, of these, because this rho sigma, A rho sigma were n squared, there is one condition. So that makes it n squared minus 1, which is a dimension of SUN, if you remember correctly. Long ago we found the dimension to be, so that is correct. Okay. With the combination relations, which I will work out, B rho sigma, B alpha beta is delta rho beta del B alpha sigma minus delta alpha sigma B rho beta. Okay. For the real form, that is for the real form, that is for SUN, a basis is, we just take B rho equal to 1 up to say n minus 1. The nth one is given by the previous ones. Okay. So there are, and then I can take B rho sigma plus B sigma rho. Let me get the coefficients right. Over 2, but I want anti-hermeticity, so I put this. Yeah. Then I write B rho sigma minus B sigma rho over 2. I think I get there's a minus sign for canonical. We'll see what they are. So if you want to go to the real form, this is how you will find this is the one which should be exponentiated to get the group, because these are the anti-Hermitian generators. But in general, when you do calculations, the tensor notation is much better, and people normally use this tensor notation, but that is using the complex. You are complexifying, you are taking this one and you are allowing all complex linear combinations, you will get that. Okay. So it is a complexified Lie algebra of SUN, but it is the complexified form. This SUN becomes some other group, some non-compact group, but never mind. Okay, let us look at what this is. This whole activity was due to Okubo. So let us look at n equal to 2. Okay. So we can write the n equal to 2, no? So it is actually I have done it directly for n equal to 3. Okay. Let me do it for n equal to 3. N equal to 2 is too trivial. Okay. So n equal to 3. Okay. I can write B11. Okay. It is A1100 in, I should say, in 3-dimensional representation as 3x3 matrices, but in general representation they won't look like this. Minus, I should take out 1/3 times unit matrix, which is equal to 2/3 minus 1/3 minus 1/3. Okay. Likewise, B22 will be minus 1/3 2/3 minus 1/3. B33 will be 2/3 will be here, get minus 1/3 minus 1/3. These are the diagonal generators, and the off diagonal generators you can write down. B12 will be, there is no trace to cancel, so it will be equal to A12 So it will be 0, 1, 0. Okay. A2, then what is it? A12, A13. It will be 0, 0, 1, etc. Then you get A23. It will be second row, third column. 1 here. And there are joins. This is a trivial calculation. Okay. Maybe I will do n equal to 2 because that will tell you something else. N equal to 2. B1, then in this case B1 in two representation, in two dimensional representation, B11. I want to tell you what this looks like in ordinary language, okay, familiar language. From that kind of expression, it will be 1/2 minus 1/2. Okay. So this is what we would call as 1/2 of tau 3. And B22, B11, B22, it will be minus 1/2 of tau 3. Because anyway the sum should be 0. Okay. Then B11, B22, then I have B12. This will be 0, 1, 0, 0. Okay. So this is equal to what? Tau 1 minus I tau 2 with a 1/2. Lowering operator, tau minus is called, yeah? And B21 is the other one. So it is 1/2 of tau 1 plus I tau 2. Okay. And if you take the Hermitian combinations, the diagonal ones are not affected. Here you should take the sum. Say if you want the Hermitian ones, take the sum, get tau 1. And the difference over I, you get the third Pauli matrix. Okay. But if you want the anti-Hermitian thing, you put some i's. Okay. It's up i's you can choose conveniently. Okay. Okay. So this is a general technique. Okay. You can do it for all group, for a symplectic group. The same idea will apply. Okay. There you will take the antisymmetric matrix and find the conditions on the group elements coming from the fact that it leaves antisymmetric matrix invariant, you will find the matrices. Okay. So this is quite systematic and quite easy. And then once you have the Lie algebra, we will discuss it as we keep going. You have to find representations of Lie algebras. For SU2, I will work it completely. For SU3, it is harder, but I will give you a reference. Okay. The person, there are techniques. The Dirac technique is very common. Okay. It is so-called Schwinger construction, which is very common. I will also mention it as you keep going. Okay. Now, to proceed, okay, we have to discuss this notion of the center of a Lie algebra. For example, the center C of L, okay, are all L in L which commute with any L prime in L. So L belongs to the center means L prime is 0, all L prime. Okay. What is the use of this? In any representation, the elements of the center will go to multiples of, so the following thing. In any irreducible representation, by Schur's lemma, okay, what will happen is any L in the center will become a multiple of identity, right? Because they commute with all the elements of the operator. I'll give you examples. In particular, okay, if Li is a basis for C, okay, in an IRR, this Li will go into lambda I times unit matrix, where lambda I are numbers. Okay. So what is the use of this? We can use lambda I to label the set of lambda i's to label IRR. This is a labeling, part of the labeling problem, but let us look at a specific example, namely this is standard example is the Heisenberg example, the Heisenberg algebra. Okay. It has a basis of 3 elements, has basis QPE with QP is equal to, I get the QP equal to E, okay, and all other, okay, brackets 0. So QQ is 0, PP is 0, E with Q or P is 0, and so on. Okay. So this is the center of the Lie. So E is, the C is spanned by E. That means C is the complex multiple of E. The one-dimensional center. Okay. We can find IRRs. An IRR is given by P going to minus I dx Ex. I should be careful. minus I times h bar dx, q going to top x hat, the multiplication operator x hat, okay, on Hilbert space. We should say the Hilbert space L2 functions on R. That is quantum mechanics. This is a quantum mechanical situation. Okay. So let me say, then let me finish it off. Then E is h bar times unit operator. So h bar can label IRR. Planck's constant is a label of an IRR. Okay. If you change it, you will get different inequivalent irreducible representation of the Heisenberg algebra. Okay. If you fix h bar, you will get only one representation. Okay. And that is the content of the von Neumann theorem, that for this algebra there is only one irreducible representation. Okay. But that is only if you fix h bar, and then this one up to unitary equivalence has only one irreducible representation which has some nice decent properties. Okay. There are actually more, but they are very bad properties. Okay. Physics point of view, they are not very acceptable. Okay. Okay. So this is a classic example. Okay. Now it is used as a, you can see, okay, Q, I should say some i's are, this is fine. Okay. Now this leads me to the Casimir operators. This is very important for the kind of Lie algebras we often consider. What are they? They are, I will not give you, they are the formal, I am giving you a quick definition, polynomials in the basis elements okay, Li of L, okay, which commute with all elements of L. I will give a more, I will indicate you what a more better way of saying it is, but let me say, okay, this is not unfamiliar to you. Okay. Example, SO3, okay, the quadratic Casimir operator is equal to summation Li squared. This square is the angular momentum. Right? This is what we call. By they commute with all the elements of Li. For SUN, or if you take SO4, What are the generators? There are two Casimir's, quadratic. What are they? One is mu nu sum. Okay, mu and nu transform like 4 vectors. So but there is another one. Do you know what it is? You take the dual epsilon mu nu lambda rho, mu nu m lambda rho. This is also a Casimir, okay, because this epsilon is an invariant tensor. So if I commute it, you will see that because of the properties of the epsilon, these are actually invariant. Okay. So this and this, okay, A and B. Okay. In fact, I will say, okay, for SO31, this is your lowest group. Okay. Actually, the connected component of this one. What happens is A becomes is like electric square minus magnetic field square. So B, I am thinking of BI, okay. So EI being M0I, BI being 1/2 epsilon ijk bj mjk. Okay. So using the m's, m is like your F mu nu, electromagnetism. So this is like the electric field, this is like the magnetic field, and one invariant is E squared minus B squared. Okay. The other is like E dot B. Right. It is analog of the E dot B that comes in electromagnetism. This is the one that leads in non-abelian gauge series to the so-called instanton physics. This one. This is a total divergence. If you write mu nu as F mu nu, then you can check that this is a total divergence. Okay? And in quantum field theory, it leads to some, well, again this pi 1 multiply connected effects, which I will talk about later. Okay. Okay. So this is another example. Okay. Third is SUN. There are n minus 1 Casimirs. What are they? Well, B rho sigma, B sigma rho. Third one is almost obvious, no? B rho 1, sigma 1, B sigma 2, rho 2, B rho 2, rho 1. So this is like tracing the B, not in the outside indices, but in the internal indices you are doing tracing. B, you are doing like this, no? Going back. Then you can have B, I don't know, rho 1, sigma 1, B, you end with rho 1 here, and here you end with rho of n minus 1. The higher ones, and this is an exercise in the higher ones, can be reduced to lower ones. The proof is by no means easy. You have to be a master of combinatorics, which Okubo is. So for SU2, For SU2, okay, B, this one, B sigma rho is actually proportional to Li squared. Square of the angular momentum. This is not different from this. For SU2, you have to change the basis and rewrite, then you find that it is the same. Okay. For SU3, you have two Casimis, which I wrote down here. Okay. This and this, the quadratic and the cubic Casimis, okay, and they come in quark physics, for example. Then it goes on like this. SU4 you get more and so forth. If you do SU5, people do grand unified theories based on SU5. That has 4 Casimis, okay, which you have to, and there is what is the use of the Casimis? In an IRR, okay. By the way, note, the above form only a basis. As their linear combinations are also Casimis. Okay. You can multiply them, add them. There is some convention regarding how you normalize them. This business of Lie algebras is, well, you have to be enthusiastic in combinatorics, then it leads to very nice results, okay, on how the whole thing behaves. In fact, Amri is deep into this. There is a book, Humphreys. Actually, this is useful if you keep going into quantum field theory and magnetic monopoles, or even string theory. They become very central. Okay, the classification of certain class of magnetic monopole states needs the structure of these Lie algebras. So this is the point. But the point about, okay, no, in an IRR. Again by Schur, okay, they become multiples, okay, lambda I times 1 of unity, right, by Schur, and we can use these lambdas, lambda 1 to label the IRR. For example, L squared becomes L into L plus 1, where L is angular momentum, and we use L to label the IRR. Okay. Now, remark. In a Lie algebra, L, okay, this is symbol, okay, L prime, L and L prime being L, is not defined. This thing is not defined, okay. So that's why I said formal polynomials, okay. So of course we deal with representations, so they are matrices, so I know what they are unit, but what do they mean, okay. So I will not do it. To give them a meaning, to give Casimis a meaning, we have to go to, we have to discuss, we have to go to the so-called the universal enveloping algebra. This is a huge thing. I don't know what to call it. They call it L hat of L and the center. Which are spanned by, which is spanned by the Casimir's. So, give me any algebra. There is something called the universal enveloping algebra. Okay, it is the way the maths people will define it is the tensor algebra of the given algebra. You go and take tensor products. Okay, so for a Lie algebra, you take this tensor algebra and quotient it by the relations coming from the Lie algebra. There is a way to reduce this huge tensor algebra a little bit, okay, by the relations of the Lie algebra. That will give you the universal enveloping algebra of the Lie algebra. Okay. And you ask what is its center? That is this Casimir's. Okay. But for us, we don't need to know this elaborate construction because we work with linear operators on a Hilbert space. So we always know what is meant by products. Okay. So for us, it is no problem. But if you want an abstract definition, you have to go through this route. It is not very useful for most purposes. It is not useful. Okay, so I will not bother about it. Okay. Now, so I have given you most of the stuff. Okay. Next time I will go a little bit more into properties of the adjoint representation and the so-called Karta killing form. Okay. That is very important for constructing invariance. Okay. So we will do this Kartan killing, this Kartan theory a little bit, looking at the adjoint representation. They are quite nice and quite easy to understand. Then we will show how to find all irreducible representations of SU2 following Dirac's method and indicate how the same method can be applied to SU3. Okay. By that time we would I can shift to tensor methods and we will recover all the representations to SU3 also by tensor methods. Okay. So we can actually combine the two to exhaust all possible representations when we are doing computations. So I stop here and continue tomorrow. Tomorrow, if you don't mind, I would like to understand, okay, let Madhusudan also come. When I should stop, people go home, I think, some of the people go home, maybe you go home, I don't know. If people are here and there is interest, I will continue up to half algebras, okay. If possible, cover it. If people go home, we can take a break, come back in January, it is possible, I am still here. Or if you feel that this is enough, I will stop. So we can discuss it tomorrow.